In this video, we're going to look at how we form enolate ions and their reactivity. So we just discussed how the alpha hydrogen is acidic. And if we want to deprotonate right away, we need a strong base to do so because these are only slightly acidic. So one very common strong base that is used for this process is LDA. Here's the structure of LDA. Whenever we mix LDA with our ketone, we can isolate the enolate ion. So what's going to happen is we will deprotonate that alpha hydrogen, and our electrons are kicked up to the alcohol. And notice the difference here between the enolate ion and the enol is that we do have a charge. That oxygen is negative, it is not protonated, so we don't have the alcohol part of an enol, so this is the enolate ion. This is going to be more reactive than an enol, and it also can be isolated. So our enols are typically not isolated, they're not typically favored over the ketone form. The enolate ion we can relatively easily isolate by adding that LDA. As a side note, we're also going to need THF, an aprotic solvent, to run that reaction in. The reason we can form this enolate ion relatively easily is we do have a resonance structure. Oops, wrong direction. We're going to kick those electrons down and put the anion on the carbon. So there's your two forms. If you have multiple alpha hydrogens on your carbonyls, they can all be removed. You can also remove alpha hydrogens from different carbonyls other than ketones, and it's all going to come down to the acidity of the respective hydrogens. So your best bet to decide if you can remove the alpha hydrogen is to look at a pKa table. So the pKa of LDA is 36. So as long as you have a pKa of your alpha hydrogen that is below 36, you will be able to remove that hydrogen. If you have a double carbonyl, those two hydrogens that are stuck in between are going to be more acidic than any other hydrogens in the molecule because it has kind of dual resonance structures that can form with the enolate ion. We also have two reaction sites on any given enolate. So here's an enolate ion. Here's its resonance structure. So when we have the negative charge on the oxygen, the reaction is going to occur at that location. We can also have the reaction occur at the carbon. So if we were to add in an electrophile, this is going to be considered the vinylic alkoxide. So alkoxide is the negative oxygen, vinylic is because it's on the double bond. So if that reacts with the electrophile, our product will look something like this. The other form is called the alpha keto carbanion. So we have a carbanion on the alpha carbon of a ketone. If we react at that site with an electrophile, it will add to the alpha position. So both positions are reactive, and depending on what reagent you're using will determine what products you get. Most of the time we are going to be doing something at the alpha position.